Hello. In today's video we're going to look at Chapter 16, Lecture 14. We're going to be going over pH for weak acids and weak bases. We're also going to be looking at percent ionization of those weak acids and weak bases, given initial concentrations and Kas or Kbs. Then we're going to be looking at calculating pHs with equilibrium concentrations and equilibrium concentrations of polyprotic acids, given initial concentration in Ka. So let's go ahead and get started at looking at the pH of a weak acid solution and looking at the percent ionization of that weak acid. So when we are given a Ka and we're asked to solve for pH, we need to do this in the same way that we calculated other K expressions using an ICE table. So I'm going to use an ICE table when given initial concentrations and Ka. Okay, so we're going to set up the ICE table like we did before, putting in our initial concentrations. We're going to base the change, or we're going to put our change that we expect to occur. Then we're going to plug all of our equilibrium values into our K expression. And these equilibrium values will have x's associated with them. Okay. After we plug this in, we will solve for K. Or sorry, solve for X using K. And then to solve for pH, which is generally one of the things we're most looking for with these, we would use pH equals negative log H3O plus. In a lot of cases, our X will be equal to our hydronium concentration. We can also solve for our percent ionization. Using the following expression, percent ionization will be equal to the concentration of HA that is ionized divided by our initial HA. This can generally be determined by taking in our hydronium concentration if we have a monoprotic acid. Okay. So, let's see if we can do this. So we've got the following solution. We've got 0.2 molar solution of HNO2. HNO2 is a weak acid. And it has a Ka value of 4.6 times 10 to the negative 4. We want to use this information to figure out what our percent ionization is and our pH. So, the expression here or our equation here is HNO2 plus H2O is in equilibrium with H3O plus NO2 minus. We don't care about water, so it's not even in our rice table. We just have HNO2 concentration, hydronium concentration, and nitrite concentration. So we start out with 0.20 molar of our nitrous acid and 0 of the other things. So minus X on our reactant side, plus X on products. And then we combine our I and C to get 0.20 minus X, and then X and X for hydronium and nitrite. We can then put this into our Ka expression, where Ka will be equal to our hydronium concentration times by our nitrite concentration divided by our nitrous acid concentration. Okay, so it's 4.6 times 10 to the negative 4 is equal to X squared divided by 0.20 minus X. Multiply both sides by 0.2 minus X and combine. Get X squared is equal to 9.2 times 10 to the negative 4 minus 4.6 times 10 to the negative 4 X, and then we're going to combine everything on one side of the equation to get X squared plus 4.6 times 10 to the negative 4x minus 9.2 times 10 to the negative 4 is all equal to 0. So we have our A, our B, and our C. We'll put this into our quadratic equation. X is equal to negative B, 4.6 times 10 to the negative 4, plus or minus the square root of B squared minus 4 times by our A, which is a 1, times by our C, negative 9.2 times 10 to the negative 4, all divided by 2 times by our A, which is 1. When we solve for our quadratic, we get two X values, 0.00936 and negative 0.00982. The negative value doesn't make any sense, so this is our X value. So we know that our hydronium concentration is equal to 0.00936, and since this is a monoprotic acid, our ionized HA is equal to that hydronium concentration, giving us a 0.00936 for that as well. Okay, so our pH will be that hydronium concentration, or the negative log of that hydronium concentration, giving us a pH of 2.03. And then our percent ionization, we're going to take the 0.00936 divided by our initial concentration of 0.20, multiply the whole thing by 100%, and we get a value of 4.68%. Let's look at polyprotic acids now. So a polyprotic acid is when we have an acid that can lose more than one proton. So an acid with two or more acidic hydrogens. So these are going to be hydrogens that are going to be attached more than likely to oxygen. Although we will see them attached to halogens as well, right? So HF, HCl, HBr, those type of things. But most of our, or all of our polyprotic acids are going to be hydrogens attached to oxygens. We can refer to them as diprotic or triprotic based on how many protons they have. So if we have a diprotic acid, we have 2 acidic hydrogens. And then if we have a triprotic acid, we have 3 acidic hydrogens. Okay. And we're going to lose each of our protons sequentially, so we'll lose one completely, then we'll lose the next one. So we're going to continuously lose protons, and each time you have another dissociation, they're going to contribute significantly less to the hydronium concentration. So second and third dissociation will contribute significantly less H plus to the H0 plus concentration. And that's because it's really hard to remove a proton from a negatively charged molecule. So, while the first one is relatively easy to remove, the second one's going to have a Ka that is significantly larger, and then if there is a third one, it is going to be, significantly smaller, and then the third one would have a very, very small Ka value. So, let's look at some examples. So, carbonic acid is a diprotic acid. The first hydrogen that is lost has a Ka value of 4.3 times 10 to the negative 7. The second one, 5.6 times 10 to the negative 11. So generally several orders of magnitude smaller for that second Ka value. Phosphoric acid, that's an example of a triprotic. The first one is a fairly large Ka of 7.5 times 10 to the negative 3. The second one, 6.2 times 10 to the negative 8. That is a very, very small value, so it's very hard to lose that second proton. And then the third one at 4.8 times 10 to the negative 13. That is a very, very small Ka, and that will contribute very little to the hydronium concentration. So, if we see over here, most of these second Kas, with the exception of sulfuric acid, which starts out as a strong acid and then becomes a weak acid, with the exception of sulfuric acid, our Ka2s are going to be considered small enough to use small x, so we wouldn't even really consider their dissociation in their hydronium concentration after losing this first one. Okay, so let's actually go through and calculate pH for one of them. So let's make sure we understand the steps. They're fairly similar to what we saw with just the weak acid example, but now we have additional steps, and then we'll do an example. So Ka is always going to be significantly larger than Ka1 will always be significantly larger than Ka2, usually 3 orders of magnitude or larger. And Ka1 is the loss of that first proton. Okay, so our second and third dissociations usually don't contribute real significant amounts of hydronium. Okay. The only example where that's not true is sulfuric acid. Our Ka2 in this case is, what was it? 1.2 times 10 to the negative 2. That's a fairly large Ka value. So we would look at that one. And the only time we actually include the hydronium concentration from the second or third dissociation is if the Kas are similar within 2 orders of magnitude. Okay, so let's try an example. We have the following acid, and when this acid dissociates, we produce the following ions. So ascorbic acid itself has 2 dissociations, and we want to see what our concentrations of all of our species are at equilibrium. So ascorbic acid itself, H2C6H6O6, those are the 2 protons that we're going to lose. So the first one looks like that, and our second dissociation, we'll take our N species here, and it will do a second dissociation like so. So, let's look at our first dissociation. We have our ascorbic acid, don't care about water. We have our hydronium and our ascorbate ion. So we start out with 0.37 molar of our ascorbic acid and nothing on the other 2 sides, or with the react products. So do minus x here, plus x, plus x. We get 0.37 minus x for ascorbic acid, x for hydronium, and x for our ascorbate ion. We're then going to put it into our Ka expression. 8.0 times 10 to the negative 5, our Ka1, equal to x squared divided by 0.37 minus x. If we are looking, we see that we can do small x here. And we get 8.0 times 10 to the negative 5 equals x squared divided by 0.37. And when we do that, we can get an x value equal to 0.0054. We can check and make sure that our small x is valid, so we're just going to do a quick small x verification, if you will. So we could take our 0.0054, our X value, divided by our initial hydronium concentration, times by 100, or our initial ascorbic acid concentration, and we get a value of 1.46%. So we verified our small x. So there is the x from our very first dissociation. Okay, then we can take and put the values that we have now received into our next table, so our second dissociation. Our second dissociation, we have HC6H6O6 minus plus water dissociates to produce C6H6O6 2 minus plus hydronium. From our last table, we got 0.0054 for our concentrations of hydronium and our ascorbate ion, so that will go in to here. 0.0054, 0.0054, and 0. We'll do minus x here, plus x, plus x. I get 0.0054 minus x, 0.0054 plus x, and then x. Our Ka2 here would be equal to our hydronium concentration times by C6H6O6 2 minus concentration divided by HC6H6O6 minus. Our Ka2 has a value of 1.6 times 10 to the negative 12, be equal to hydronium concentration 0.0054 minus plus x times by x divided by 0.0054 minus x. Because of how small this value is, we can use small x, and we get 1.6 times 10 to the negative 12 is equal to 0.0054 times by x divided by 0.0054. And our x will be all that's left on the right side once we cancel 0.0054. So we get an x value of 1.6 times 10 to the negative 12. Okay, so we can now use all the values we got for our x values, our x1 and our x2, to solve for all of our concentrations. So H2 C6H6O6 is equal to 0.37 minus 0.0054, our first x value, giving us a value of 0.364 molar here. Then we have HC6H6O6 minus equal to 0.0054 minus 1.6 times 10 to the negative 12. So basically no change there, giving us 0.0054 molar for that one. Then we have C6H6O6 2 minus equal to 1.6 times 10 to the negative 12. And lastly, hydronium. The first dissociation is the only one where we got hydronium concentration worth anything. So we could add in the next one, but again, it makes no difference. We'll still be at 0.0054 molar here. Now we can take the pH equal to negative log hydronium concentration, which gives us negative log 0.0054, giving us a value of 2.27. So, as we saw from here, our second dissociation was significantly smaller than our initial dissociation. So, or the Ka value was significantly smaller. Therefore, we didn't see any contribution to our hydronium concentration here from our second dissociation. And that's what you should see. Now, that's different if we have something like H2SO4. So let's try an example with H2SO4. So H2SO4 is diprotic. It'll have two dissociations. The first one, H2SO4 plus water, will completely dissociate, one-way arrow, to HSO4 minus, which is a weak acid, and hydronium. So this occurs completely. So whatever our H2SO4 concentration is, it'll be equal to our initial concentration of HSO4 minus and hydronium concentration initially. So these values can then be put into our first ice table that we'll use. So H2SO4 is equal to 0.37 molar. So it's going to completely dissociate to produce our initial concentration of HSO4 minus and H3O plus like so. So those will go into our table. 0.37, 0.37, and then 0. Go minus x plus x plus x. We get 0.37 minus x, 0.37 plus x, and then x there. This will then go into our Ka2 right here, where we have Ka2 is equal to H3O plus concentration, SO4 2 minus concentration divided by HSO4 minus. So we have 1.2 times 10 to the negative 2 is equal to 0.37 plus x, 0.37 minus x. We have a fairly large value, so we will not be able to do a small x here. We're going to have to actually solve for this. So when we multiply across and combine things on the multiply across and then combine things on the right, we get okay, one second. (0.00444) minus 1.2 times 10 to the negative 2 when we multiply both sides by 0.37 minus x. And that's going to equal 0.37x plus x squared. Okay, now we're going to combine. I'm going to go on to the next page. We're going to bind everything onto one side of our equation, set the other side equal to 0, and what we get is x squared plus 0.382x minus 0.00444 is equal to 0. We can then put this into our quadratic. X is equal to negative b plus or minus the square root of b squared minus 4 times by a times by c divided by 2a. When we solve for that, we get two x values, 0.0113 and negative 0.393. Can't be negative, so it has to be this value right here. So now our x value is 0.0113. We can then place it into all three of these and solve for our concentration. So first, H2SO4 completely dissociated. So at equilibrium, we have 0 molar here. H2SO4 minus. We started out completely dissociating into it, so we have 0.37. And then we removed 0.0113 molar of it, giving us 0.36 molar. Then we had SO4 2 minus equal to X, so it's equal to 0.0113 molar. And we had H3O plus concentration equal to 0.37 plus 0.0133, oops, sorry. Zero point 0.0113 molar, giving us 0.38 molar there. And now that we have that, we can solve for our pH. pH is equal to negative log 0.38, giving us a value of 0.42. Okay, so that's everything for this lecture. I will see you guys later.